Okay, welcome everybody. Thank you for joining us this evening. Dinah unfortunately could not be here, so I have the pleasure of introducing Travis this evening. I am Jen, I'm director of the detection team, and I get to work with Travis often as he tries to make sense of the large amount of data that we have and making it, grouping it logically and turning into something we can actually use, trying to make sure that the machines are doing what they do really well and the humans are doing what they do very well. So welcome Travis, and thank you. Afterwards there will be there's at least one announcement I think afterwards, so please stay tuned. Thanks.
All right, so this is my first talk in this venue, so I just wanted to have a quick show of hands. How many people here have used machine learning before? All right, a few of you. How many people work in cybersecurity? Unsurprising. So I'm going to be touching a bit on both, so if you have any questions on either of those as I go, just let me know. And if you can't hear me, also let me know about that. I'm going to be mainlining calls up here, so I'm going to try to speak clearly, but I may start getting quiet throughout the night. All right, so we've all heard the hype before. Security plus artificial intelligence gives us better security. You could replace security with pretty much anything, and that's the buzz right now. But there's this question as to why it's the buzz. Why are we looking to artificial intelligence to solve our problems? Well, it'll help us solve the people problem. Cybersecurity is known to have a resource shortage in terms of people who know what they're doing. And so if we could have machines know what these things are, then we'd be able to help fill that gap. There's also employee retention. A lot of what we do inside cybersecurity is routine. We're looking for the same sort of exploits across all of our customer base over and over and over again. If we can automate that, then people won't have to burn out quite as much, and they'll be dealing with the more interesting problems. And on the flip side, the things that we do routinely are the things that machines are the best at automating, because we have lots of data about how we should be automating them. It should also help us solve the security problem. Machines are fast. And technology can run 24/7 without tiring, whereas humans have to sleep. I know I was trying to get over this cold today. It can also help with improving accuracy. So humans get bored of routine tasks, we get tired, we start making mistakes. And it should probably go without saying, but you should only automate tasks where the machine is actually going to be better than the human. So as a result, detection accuracy should increase. It will also help us with cost. So in general, machines are cheaper than humans. And the cost of machines will drop over time as we start getting improvements in hardware, whereas human salaries will increase due to cost of living and other things. Again, you should only try to automate things where machines are going to be cheaper than humans. For example, you probably wouldn't get some sort of receptionist bot in order to do all that, because first off, they're only going to do a narrow set of what a receptionist does. And second, it's not much value there. It's probably valuable in the case of a hospital, for example, where there's the potential spread of disease, and reducing that would be valuable. But outside of that, I would not recommend that we all just replace that tonight. There's also scale. If we start replacing humans with machines, that will help the overall cost scale sublinearly, because you get efficiencies in the scale. And then it also starts you down the path to replace more and more of your functionality with machines, which again will improve as you scale. So by this point, I hope I've all convinced you that AI is great, and we should just replace everything with AI. At which point, there's the obvious question of, why do we need humans? So humans help us on the novel side of things. If there's small data, for example, machine learning requires large amounts of data in order to find these patterns, whereas humans can find patterns in very small things. Humans are also great with new threats. If there's 0 days, for example, they can start to detect them using new techniques. They can also understand the theory behind these in order to do that. They could also look at third-party resources like blog posts or podcasts in order to understand what new threats are coming up, and then incorporate that into what they're looking for without requiring having seen it before. Then there's also things that on a per customer basis. So each network is different, and humans are better at generalizing across those things to say, well, this particular network is for some sort of web scale server where they're going to be serving up content 24/7, whereas this one should be completely internal and nothing should be accessing it. And on top of that, you may not have everything in the machine consumable format. Like I just said, those particular instances may not be in some way that the machine can then incorporate that into its model of what should be accessing different things at a time. So it's not so much about machines versus humans. First of all, it's a spectrum. We can be anywhere along there, and we should probably strive to be towards the middle and get the best of both worlds. In the future, machines may be able to completely replace us, but that's not where we are today. So we're going to go through this formula. We're going to try to define the problem and process that we're going to be trying to replace. Then you want to inspect and clean the historical data that you already have in order to make it so that you can actually train some sort of model on it or use some sort of other automation. Test various automation techniques on it to find out what works the best and what parts can be automated. And then finally, building this feedback loop in production. So throughout this talk, I'm going to go through these steps in general, but I'm also going to go through a concrete example so you can see some of the nuances here. So step one, we have to define what we're doing. So what tasks are we trying to automate? We want to be able to define this as concretely as possible. And to help do that, we should know how users currently do this task. So you need to be able to document all the steps involved. Now, some of those steps may be nebulous. It might be, well, I look at this thing and I know that it happens to be ransomware. That's okay. But knowing that they go through these steps to get to that point really helps you get what the steps are and which ones could be automated. And also what data they're looking at. And at that point, once you define all these different steps, you can then start to figure out which parts you want to automate. Some of them you might just be able to remove. You might talk to 3 or 4 different analysts, they all do it slightly differently, and then from there you go, well, here are the 5 steps we actually need to do, and so you guys can discard the ones that you're doing that are in addition to that. You can also start to see which ones could be just completely automated, or maybe some of them could be partly automated, or some of them could just be augmented. Maybe there's data that you could just show them that would then remove the step. So you could incorporate, say, GUIP information. That might be something they're mainly looking at right now, but if you're able to stamp that on things directly, then they don't have to go to a third party. So.
Sorry to interrupt, sorry, I meant to announce that I was being recorded. You guys may have to notice, but just so everybody knows, the presentation is being recorded. Sorry for interrupting.
So for our example, at Arctic Wolf, it may come as no surprise that we ingest external threat intel sources on a daily basis in order to give our customers the best security that we can. Some of these sources need additional classification. So specifically, I'm going to be talking about the emerging threats snort rules feed. They just come in and say, here are all these different things, here's what they mean, and that is rather nebulous. And so for us, we particularly have an SLA around ransomware. We say that within ransomware occurring in your network, we will alert you within a certain period of time. And so for us, we really want to know, is this rule detecting ransomware, or is it detecting something else, like a phishing landing page, for example? And then we want to update that list of triggers to say, these are the ones that are ransomware, these are the ones that are high priority. So given all that, I knew I had some questions at the time. I had very little security background, so my first question is, what does a snort rule look like? Well, this is the start of a snort rule. It actually goes off the slide to the floor somewhere. There's a lot of technical pieces in here explaining what it's looking for inside of the packet. In some cases, it's looking inside multiple packets. And there's a lot of things here that just aren't very useful to try to learn from. So perhaps a better question is, what do security analysts use 90% of the time to say if this is ransomware or not? And that's this. There's a very short description of it that includes the first part is the snort ID, so you need an identifier for the rule. The second part is the description, and then after that part, there can be URLs, there can be web hashes, there can be a bunch of other things. But primarily, they look at the description of the rule. And as you might notice here, that description includes the word ransomware, which is probably a pretty good indicator this is a rule that detects ransomware. How do they see new rules? We'll leave this all incorporated into Git. So they can do a git diff on the file, find out what has changed in the last day, and then sift through that. Now that's not a great interface. As you can see, this is just one section, and there's other pieces of context around it. And so on this particular day, there were about 60 rules that changed. And so those are all in different blocks that they have to sift through and make certain that they're looking at all of them. How many rules are there per day? Well, I mentioned that on this day there were 60. I did the calculations. There's about 41 new rules that are coming in per day. That being said, that's net new on average. That doesn't count cases where there's things that are added and then deleted. And so there's lots of nuances in this. Then finally, and perhaps most importantly, how do they flag one of these rules as ransomware? Well, it turns out there's another file, and that file is just a list of SIDs. And all of those SIDs are manually input, and those are, for this set, the list of SIDs out of that 60 that I mentioned, which were ransomware for that day. So, given now that we've seen the whole process, we can quite quickly find some problems with it. So new snort rules can come in multiple times per day, but we're actually only checking once per day, which isn't great. That means that there's a delay between rules coming in and when we actually say that they're ransomware or not. There's no way to track if a set of rules were checked. So we have that one file that lists all the ones that are ransomware. That goes through a PR process when it's changed, and so we get some sort of review at that point. But if, for one day, for whatever reason, there were no ransomware rules, there would be no PR that would then be checked by a second person, which looks the same as if nobody checked the rules, because again, there's no auditing around it. The majority of time, this is a mundane task. They're looking at the description, they're looking for a few keywords to try and pick this out. It's not that hard to do. Sometimes they do actually have to look at the rule because people put in bad descriptions on it, or they need to do more research and look up some third-party blog to go, I've never heard of this word, what is it? But most of the time, this is a rather boring task. And we have found some mistakes in classifications. So the fact that they're committing just a list of numbers is rather obtuse. In order to actually review it, you have to then go and bring up, here's the list of all the rules, what's the description for it, okay, yes, that makes sense. And on the flip side, you can't see which rules weren't classified as ransomware. You'd have to bring up, here's the diff each day, here's all of the ones that were added, here's the ones that we said were ransomware, did we miss anything? So there's lots of concerns there. Do we need machine learning? So we just listed all those problems. That might come as a bit of a surprise because the whole description talks about how we're going to use machine learning, but it's a valid question to ask. Code is great. Code is human understandable, except for maybe Perl, as was mentioned earlier. It is directly debuggable and fixable. If you find something that's an off by one error, you can go in and fix that. You have that in your machine learning model, it's much harder to debug. It's resource efficient. You're writing code to do a specific purpose, as opposed to having it try and figure out what you want it to do. You can directly capture the knowledge that you want to put into it because you're coding it. It can tackle problems with small amounts of data because, again, humans see what the thing is, they put it in code, they solve the problem. On the flip side, machine learning can solve problems we can't. I would not know where to start in order to implement facial recognition, but I can give it a whole bunch of pictures of people and have it solve that problem for me. It can indirectly capture our knowledge just that way. Again, I can recognize faces, but I can't tell it how to do that. And it can also find patterns we didn't know about. So, for example, Google has created AlphaGo, which is now the top playing player at Go. And they're now learning, players are learning from this machine new techniques that we didn't know about before. So, let's go through this. New snort rules come in multiple times per day. We don't need machine learning for that. We could just throw more people at that, have people look at this 24/7. That's going to incur a cost, but it is solvable without requiring machine learning. There's no way to track if a set of rules were checked. Well, that's not going to be solved with machine learning. That's a process problem. And so that's going to be solved by improving the process and workflow. The majority of the time it's mundane tasks. That could be solved with machine learning, doing some of the lifting, but there might be other ways we could do it too, as we'll touch on in the next point. And we found mistakes in classification. Well, if we track what's reviewed and show the description with the SID and make certain that everything's being audited, then that second reviewer could catch a lot of these mistakes. So we might not need machine learning. On top of that, maybe we just set up a very simple rule where we check, does the word ransomware appear in the description, and then say it's ransomware. Maybe that's all we need to do. That's not machine learning. So we might be able to short circuit this early. So to summarize, you want to be able to scope the problem, actually define what you want to do. You want to review the process that your security analysts are doing in depth, split that process down into individual tasks, determine which of those tasks you want to solve, and then look at how you might solve each of them. And once you've done all of that, where you fully understand the problem, then you can review if you want to use machine learning. Now, it might come as a surprise, but we are actually going to use machine learning here. So, should we use it? Well, the big thing is the security analysts are using the description 90% of the time to determine if the rule is ransomware. So there are a couple ways that we can tackle this. We could just check ransomware in the description or a series of other keywords, or we could use something called natural language processing in machine learning to actually try to understand what those words are itself and then build up its own corpus. So what we should really do is try both and then see which is going to be best. Which moves on to part 2, inspecting and cleaning the data. So, what data do we have? That is a very important question, and what format is it in? Because most likely it's not in a way that we can use this for machine learning or for whatever other task we want to use. So we're going to have to understand that and then transform it. Is it usable as is? How do we need to clean it? There may be some situations where it needs to be improved in some way, that it's missing some key feature that your analysts will be using and it's not present. Then you want to do just some open data exploration, which we'll get to in a moment. And you want to fix incorrect data. There will inevitably, with any sort of people process, be some sort of problem with how things have been classified or done in the past. That's not a knock against who we are. That's just the nature of, if you do something for long enough, something will go wrong. And then finally, given the data, can we actually solve the things we want? Can we automate this? And here we want to really define concrete goals. So far we said we want to automate this, but what does that actually mean? And we'll touch on that in a little bit. So, back to our example, what data do we have? Well, we've already seen this before. So we have the data in a specific format. It has the snort ID, the description, and then other things after it, all separated by 2 pipes. We have this other file that has a list of all of these things that are ransomware by their snort ID. And so we can just correlate those 2 things together, and we're good. We can also see that there are about 42,000 snort rules at the time that I was doing this, and that about 1,200 of them are, or sorry, 1.2 thousand are labeled as ransomware, so approximately 1 in 35. That's important for people who do machine learning because that's a bit of a class and balance problem, but we can talk about that afterwards if you are interested. So, is it usable as it is? Yes, it is. In order to actually use it, we just need to do some light parsing. So this is actually really nice and doesn't happen that often. So I'm very pleased that we can just skip past some of that. Is there any incorrect data? Well, it's really hard to say. There are 42,000 rules here, and I'm not going to go through them one by one to try and pick them out, and I also don't have the security expertise to go through them one by one to pick them out. So we're going to have to figure out a way to deal with that. So the next thing to do is we're going to explore the data. So the first thing to do is you want to actually know what you're dealing with. So we've already done our accounts, which is good. And then we want to actually look at what these rules are. So let's just grab some sample rules. So here are 7 that were classified as ransomware from before. And already, as we mentioned before, we can pick out a few things, like the word ransomware. Interestingly, that only appears in 5 of them out of the 7. So ransomware is not going to be enough on its own. We can also pick out the word lock. Now that's actually a substring in some of these. Locker or locky is present. On the last 3, we actually get some sort of pairs of words, CNC check-in, so maybe that will be useful. There's also cases where words appear in 2 different formats. At the top, you can see that there's onion capitalized, and then there's also .onion. And further, there's the pair of onion domain, and sometimes they're adjacent, sometimes they're not. So there's lots of questions there about, are those useful features? Are there things that we should be treating them differently, etc. And that's something that you'd have to talk to your security analyst, your expert in this field, to know about. And finally, one last thing, you can actually see that the first 2 rules are the exact same for their description, just the number's different. So that's just useful to know in case you could then do a really quick pass to see, are there any rules with the same description that are classified differently? One was ransomware, one was not. And then there were 53 rules that were not ransomware on that day, so I just randomly picked 6. So a few things we can learn here. These have some sort of a URL there. So we probably want to be able to handle that in some way. That's not a key feature, the rest of the description is. So some way to filter that out. Similarly, down here we have 2 rules that just differ by a port number. Again, probably not that important. We also see CNC on these rules. In fact, CNC is so popular that some rules have it twice. So that's probably not a great thing to say, well, if it has CNC, it's automatically ransomware. And we can also see that check-in appears as well. Now, because we're mainly security audience, we all know that that makes sense. CNC is command and control, and having some sort of a check-in is a normal thing of a lot of different malware. So it's not surprising that that's not unique to ransomware. All right, so job done. We looked at 13 rules. Well, I guess there are 42,000, so we should probably do something a little bit better here. And one of those tools to look at these larger data sets is known as a confusion matrix. So I'm going to give you a small example of that with the word check-in. So let's say we wanted to create a rule to classify things as ransomware or not, and we're going to release it in production. So we're going to say, does it have the word check-in? And so we saw that for the 7 rules that were labeled as ransomware, 3 had that word, or didn't. And for the ones that were labeled as not ransomware, only 1 of them had that word. And so that ends up with this. We have totals of how many words have the word check-in, how many rules do not have the word check-in, whether they're not the ransomware, and the totals there. Are there any questions so far? All right. Yes.
So the first one is the title of the rule or the detail as well?
The description that we were looking at. So where it said like CNC check-in, if the description had check-in in it. All right. So from that, we can calculate a few things. The top number there is if it said that it was ransomware because it had the word check-in in it, it would be right 75% of the time. 3 out of 4 of the rules that had the word check-in in it were ransomware. If it said a rule wasn't ransomware because it was missing the word check-in, it would be right 56% of the time. 5 out of 9 of the rules that did not have the word check-in were not ransomware. But perhaps the most important metric for us is recall, which is the percentage of rules that it would detect. In this case, it only finds 3 out of 7 of the ransomware rules, less than half. So this is not going to be a great way to detect ransomware. So that's just looking at the 13 rules we manually inspected. Let's say we scale this up and use the word ransomware. Well, these are the numbers that we end up with. 70% of the time that a rule has the word ransomware, we consider it ransomware. Okay? Perhaps even more surprisingly, only 31% of ransomware rules have the word ransomware. I'm a little bit confused. So the best thing to do in these situations is to look at what we got wrong. So the top set are cases where a rule is ransomware but does not have the word ransomware in it. And we can see the first one has ransom. Okay, that's probably still ransomware. I can understand why we missed that. The second one has crypto. Okay, that's another keyword. And the third one has server. So server is a type of ransomware, and that should also be something else that we consider. But we're kind of playing whack-a-mole at this point. At the bottom, though, these are things that are not ransomware, but have the word ransomware in it. Turns out there's a lot of these. These particular ones, they're a problem because they're just so noisy. They are, in the majority of cases, vast majority of cases, not ransomware. And so it's not worthwhile to have them alert immediately because it's just far too much noise in comparison. But the takeaway here is this is not a great first result of just trying to use that. Sorry, is there a question in the back?
So when you came up with the confusion matrix with the 42,000 rules,
Yes.
are you just looking at all of the SIDs that somebody's manually put in? Like how do you know that, say, something has ransomware but does not contain the word ransomware? Like, is that coming from the manually
Yes.
checked in stuff, or is that something else?
That's from our security analysts reviewing these rules over time.
And so you're trusting that they got every rule right?
Right now, yes. That is a very good point. So we'll touch on that in just a moment. So the next thing we want to do is compare this to machine learning. And so we're going to build a very simple machine learning model right here because we just want to see how the data does with it. So we're going to do this very easily. We're going to make everything lowercase. and then we're only going to use full words. This is known as a vague words approach, which will deal with the onion problem from before, where it's capitalized or it has punctuation, etc. We're going to use k-folds with k being 5 to get our train test splits, which I'll go into a bit more in a little bit. And then we're going to predict the classification using logistic regression. And logistic regression is a very simple model. What it basically does is it assigns a score to each of those words. That score can be positive or negative. It then takes the sum of all of those scores across the entire description. And if the total score is positive, it classifies it as ransomware. If it's negative, it classifies it as not ransomware. And these are the results. So we can see that it's doing a lot better. When it predicts something is ransomware, it's right 94% of the time. When it predicts something is not ransomware, it's right 100% of the time, which is just a rounding error. If there's a rule that's ransomware, it catches 88%, which is not great, but these are all better than what we were doing before just by looking for the word ransomware. So we're definitely off to a good start. But I'm still interested in what it got wrong, so let's take a look at those. So going through this, we're going to look at 4 different cases. At the top, we're looking at that it was ransomware, but the machine learning model predicted that it wasn't. And so for this first one, it turns out, I got the events happening a little bit off. That's okay. So the first one, this was a situation where the model was correct. This is something that should not have been ransomware. It was incorrectly classified. And if you remember from before, the way the security analysts did this was they would put in what the SID was. And so it's entirely possible that somebody just transposed 2 numbers or did something else. And so that's why there's now something that's being flagged as ransomware that shouldn't be. The second one, the model said shouldn't be ransomware, and it was wrong. Turns out that SAMHSA is a type of ransomware, but it was relatively new at the time. So the model hadn't seen it before and didn't know that was a key word to say this is ransomware. For the bottom 2, it got the first one right. That is ransomware. It has the word ransomware in it. And that was just something that was missed. Again, there are 60 or 70 of these per day, and so it's entirely possible that somebody just skims past one and misses it. The bottom one, the model got wrong. Trojan, C2, and domain are all very popular words in terms of looking at ransomware, and so having them present in there, it actually has Trojan twice, would be enough to push it over that threshold and say that it's ransomware, even though this wasn't actually the case of that. However, this is enough for me to want more validation from the security analysts. So this is the point that the person in the back was mentioning. We want to actually check that the first pass that these analysts did was correct. And so we can use machine learning to help verify this. So, getting into what k-folds is. What we do is we take all of the data that we have and we split it into, in this case, 5 groups. And we're going to train a model on 4 parts of that and have it predict on the 5th. And we do that 5 times. In each case, we take a different piece that we wanted to predict on, train on the other 4, have it predict on it. Now, I've visually shown this here by splitting the data vertically. But I could have just as easily split it horizontally. And this is actually important. So in order to get really robust predictions, we want to do this multiple times. Let's say I want to validate this data. I want to see, did they get it right? So if I split it vertically, then I'm taking this set of data, train on it, and then predicting on that one set. And then if I split it horizontally, I'm now training on this data and testing on that. And in doing so, we've placed 20% of our training data, which means that the machine learning model will find different patterns potentially in that data and then give different results. It's kind of like this GIF. So this is a bullet time camera from the release of a video game. And as you can see, at certain points, for example, one of the people's shoes completely obscures the woman's face. And so depending on which frame you're looking at, you get different information. And the same is true of doing all these different shuffles with our data. Depending on how we look at it, we can find different patterns there. And I kind of drive that point home. Can anybody read the text on the back of the screen? Yeah, time is power, quantum break. It was only by being able to see all those different images together that we were able to actually pick out that larger pattern there. So we do the same thing here. We're going to shuffle the data 200 times. Each time we shuffle it, we're then going to do k-folds on it, split into 5 groups, predict on everything, and take the things that are consistently misclassified, those top things, and send them off to be reviewed. Then we have those results from our security analysts. We're going to store that, update our data that we had, and then we're going to make certain that we don't ask them about that again. And that's important because we're then going to do this all over again. Now that we have these new things that we found that were wrong, we might find new patterns in there that will alert us to even more inconsistencies. So we just keep doing this over and over again until we finally hit a point of diminishing returns. Yes.
Are you testing the model on the 5th subset of data? Do you cleave it off and then leave it almost virgin, and then you're testing the model to see how accurate it was?
Yes, exactly. And so in this case, we're not necessarily testing how accurate it was, more of what is the inconsistency between the two, and then trying to understand why there's the inconsistency. And so at the end of this, we ended up with 243 new rules that we classify as ransomware, and we took 30 ones that were pre-classified as ransomware and devoted them to not ransomware. Which raises the question, how good are humans at identifying ransomware? So we can go through the metrics and do that calculation, and then we can also do the same thing for machine learning, and then we can compare the two. And you might jump to the conclusion that, well, obviously the machine learning has better results here. We should just switch to machine learning. But I want to caution you here, these are idealized numbers. We went through round after round after round of trying to polish this data to be as pristine as possible. Production isn't that clean. There's going to be situations where humans are going to find new things that our machine learning model won't. And so we shouldn't expect for these particular results to be replicated in production. So like I said before, we're looking to merge these two things together. Humans are good at new threats, machines are good at established patterns. We should get the best results by merging them together. So, that leads us into setting concrete goals. We're going to have a machine learning system initially classify rules, but we only wanted to classify the things that it's certain of, which we'll get back to. Anything it's uncertain of, we want to leave for a human. Now, what is certainty? In this case, we're going to say that if the model says something is ransomware, it better be right. And we should put a number to that and say that it has to be right 99.9% of the time, which is a very high standard, but we'll see if we can do it. And then we're going to do the same condition for not ransomware. If it says that it's not ransomware, it better be right 99.9% of the time. And then anything that it isn't this confident in on either end, we're going to label as unclassified or uncertain. Any questions? All right. So to summarize, you want to understand the data location and format. You want to be able to actually inspect the data manually and programmatically to make certain that everything makes sense to you. Then you can build simple machine learning models to check for bad data and then have experts review those inconsistencies. And at that point, now that you have clean data, you can then determine if you want to replace or hybridize your process with code or machine learning, or perhaps both. And then you can actually set concrete goals about what you want to accomplish. Which brings us to part 3, testing automation techniques. At this point, you might have a face like this. Didn't we just do that? We were just using machine learning. What are we doing here? Well, we used very simple automation techniques to try to clean the data. We were just using one particular model to test this out. That doesn't mean it's going to be the model that works the best, and you should try various models to see what's going to work. And you should also try other code solutions. Maybe there's a list that you can come up with of different words that would work well enough for your purposes. You should evaluate their effectiveness. So we have those concrete goals. We should see how well they accomplish those. And then if we're going to design a hybrid solution, which is what we're currently trying to do, we need to set thresholds. We need to say, when are we going to trust the machine? Are we going to trust a human? When are we going to require both to weigh in, etc. So, in terms of the machine learning side, there are lots of things you can do here. I will just briefly go over some of these. So in terms of features, you could use full words, which is what we did for cleaning the data. You could use pairs of characters. So that would help you identify things like block, because you'd look for LO, OC, CK. And if all three of those happen in a particular sentence, then that's a higher probability that it's going to be ransomware. Lemmatization is looking at the root of a word. So that's taking running and ran and converting it to run. So that may be useful in certain situations. Embedding starts trying to find nouns and adverbs and different context, S around what the words are, and there's a bunch of other things there. And then you can look at different models. So logistic regression is what we did when we were cleaning the data. There's also things like decision trees, neural networks are all the buzz. Recurrent neural networks are very good at text. Or you could just steal somebody else's model and use that. So BERT is something that Google put together, and then Facebook took it and created Roberta, and it's supposedly better now. So I'm sure that there's going to be an arms race on that. But the key thing here is when you're evaluating your model, you want to replicate production as close as possible. So there are a plethora of cases where people have built some sort of machine learning model, they've tested it on their clean data and went, this is perfect, look at how good this is. And then they get in production and there's a problem. The problem is they haven't replicated what they actually do in production, and so it falls apart. And this is an issue across all sorts of machine learning things. Tesla, for example, is going so far as to create simulations of actual real-world environments to simulate their driverless cars in to make certain that they're going to work. You probably don't need to go that far, but you should try to replicate production as close as possible. So that raises the question of how are we going to do this in production? So for us, we have our historically classified data. We're going to generate some sort of initial model on it. Then we're going to get our new snort rules in. Our model is then going to predict if it's ransomware, not, or if it's uncertain of what it is. Then we're going to have our security analyst review all of those things. And with its overrides that the human puts in, we can then update the model, learn new things, and then repeat this process. So given all that, what we should do is we should break the data down by commit so that we have it ordered in terms of when those rules appeared. We should get, say, the last 100 commits or so, and then we want to test on those. We're going to train our model initially on everything before that. We're going to take the model, simulate predicting on the next commit, see what it predicts, then allow for human correction, which is going to be using the labels that are already there, see what it got wrong, and then update the model saying, well, now you have this new data, humans corrected it, train the new model, and then predict on the next commit. And then do that for all 100 commits. And at the end, we can then see how well it did at each of those stages and see overall what we should have set our thresholds at, if it's successful, and go from there. We're not going to do that. And the specific reason we didn't go forward with doing that whole thing was because, first off, not doing it, there's an easier way to set it up using k-folds, which we already had done for cleaning stuff. Two, the way that we actually want to do this is going to give us more robust thresholds, which we'll get into in a moment. And we didn't expect there's going to be a huge difference between the two. We expected that doing it in this particular way was going to simulate production close enough that we didn't have to go through the strenuous task of trying to deal with Git and everything else there. So what we're going to do instead is we're going to use k-folds again. We're going to change it slightly to be 10 instead of 5 before. We're only going to do 100 shuffles. But what we're going to do is we're going to, each time we shuffle, we're going to calculate the score on the data we predict. Then given all of those scores, all 10 folds and all 1,000 shuffles, we're then going to try to determine what thresholds we should set so that when it says that it's ransomware, it's right 99.9% of the time. When it says that it's not, it's right 99% of the time as well. So that kind of looks like this. And let me explain. So at this point, the model has gone through and scored to these as whether or not, it's just given it a number, let's say. And that number, the higher it is, the closer it is to the left, the lower it is, the closer it is to the right. And then we've gone in and actually said, which of those things that it said, which of them are ransomware, which of them are not. So it's actually done a pretty good job in separating the orange from the blue here. But you can see that there's that gradient in the middle. Each of these rows represents one of the 1,000 shuffles that happened, and so all 42 rules there are sorted by their score. So what we want to do now is we want to say, where should we draw a line so that 99.9% of it on one side of it is what we're looking for? So in this case, we draw one line there, and then everything above that threshold are ransomware, 99.9% of the time. And similarly, we draw another line, and 99.9% of the rules below that threshold are not ransomware. And then the remaining 23% of the rules in between there are labeled as unknown. So, determine how you want to evaluate your models. We did that, and we said we wanted to do it based on how accurate they could be in actually predicting these things. We then set up the evaluation there and figured out how we're going to actually rate our different models. We created various models. I did that in the background. I didn't decide to go into it. And then in hybridizing, we calculated the thresholds. And so we have specific values now that we say it comes in above this line, we're going to say that it's ransomware for certain. It comes in below this line, we're going to say it's not. And everything else we're going to leave for a human to review. We actually went a bit further, and we still gave it the prediction of whether or not we thought it was ransomware or not. But we didn't say that we were certain about it. So that still gave the humans some insight into what the machine thought, and then potentially that could be used for additional stuff. And after we did all this, when we went through all the different models, we could pick the winning model and go ahead with that. And so in this case, it was a machine learning model that won. Which brings us to the last step. Now we have to get this out there. So how are we going to build this feedback loop in production? Well, feedback loop in general is you want to give the model access to historical data, train it on that historical data, have it predict on new stuff, save whatever it predicts, have a human able to override those predictions, save what it overrode, and then periodically you want to train a new model on that data so that it's always up to date. In security especially, these things change all the time. And if you aren't constantly learning these new things, you're going to be out of date. Then we need to deploy this whole thing. So, as we touched on before, this is the loop that we want to build. Now, in terms of steps, we're actually doing decent here. We've already done 2 of these before in the completely manual process. We have a way to get these new snort rules down, and we have the security analysts reviewing all of them right now. So we already have 2 pieces out of 6 in terms of our workflow. So we can build on those. When we're downloading those new snort rules, we can actually have access to all of them at that time, and we can train a model on all of the old data. At that point, it can then predict the new rule classifications on the ones that it just downloaded, and then it can save those new rules and the predictions together, which helps with the auditing problem that we were mentioning before. Then we want to deploy that. As we said, it's going to be certain about 77% of the time, and we want those out in production ASAP. So we don't wait for a human to verify them, we just send that out. And again, we're confident that it's going to be right 99% of the time. Then we want to have a security analyst review. So they want to be able to save their overrides, if they override it, or in the cases where the model's uncertain, whatever they say. And then there's going to be a manual PR review after that. We already have the manual PR review figured out. But now, because we're saving the rules and the labeling together, we have a much more robust review process, at which point we deploy again. Any questions?
How do you know which models to consider? You take them all and do all the process, or you, depending on type of data, you target specific range of models that there is?
So it is a bit of both. You can definitely do a shotgun approach, but that's going to be more costly, obviously. So what I personally like to do is go in with a few ideas. So for text, for example, there are certain ones that are for image processing, like convolutional neural networks that look at pixels that are near each other, which aren't great. There have been some people who have done some stuff there, but they aren't so good for text. So I probably wouldn't use that one, but if I was doing image processing, I would use it. And so there are a few initial candidates, but even with that set of initial candidates, you then want to look at what features you're using. So in image manipulation, you might just use the raw image, but you might also split it in certain ways. In text, you're talking about just taking words or doing different things there. But then on top of that, there's other things in terms of like the size of the neural network you might want to use, or various other things that you want to tweak with it. So you initially come up with a set of models that you want to try, and then it's usually a lot of iteration from there.
I know it's if this is applicable, but I know Microsoft, they are working in their machine learning stack to do automatic model selection, where they fire all the models and they should suggest you which one they think is suitable.
Yeah. Amazon's doing something similar with time series prediction, where they try all the different models and figure out which one works the best. There are advantages to that in terms of you don't have to think about it, but it does come at quite a cost. We tried that at one point with the Amazon solution, and it was quite costly just to have it try everything. Whereas we would be able to just manually say, well, this half of the models don't make any sense to try, and weed it away just from the start. So just a few final notes here. We actually went through the process of updating our model constantly. It was cheap to train. It only took about a minute to do so. It helped us learn new types of ransomware as they appeared, and we never needed to check if we needed to retrain. The way that you would normally do this is you would say, how well is it classifying things? Is there some sort of decrease in the metrics I'm trying to track? If there is, then I should retrain. But that means that you have to start setting up a separate retraining cycle, because retraining can usually take a long time, so you don't want to do that in line with all the other work you're doing, and so it can add a lot of complexity. So it's nice to just be able to avoid that. That being said, there are lots of nuances here with online models and drift detection and all these other things. So definitely do your research before going one way or another. That being said, we did check if our model was still good. So even though we were training it on a daily basis, there are situations where that we're looking at full words, and maybe full words no longer were important. We needed to look at substrings of words or other things. So what we did was we actually split the historical data into various things, trained it on, again, part of it, to test it on the others, to see, is it still doing okay? Are thresholds correct? Because we set these thresholds, we trained them years ago. Is it still doing what it should be doing, or is it now failing at classifying things well enough? And so, because we're only doing this on one shuffle, we set our threshold slightly lower, because that shuffle might be a bad one, whereas before we're looking at 100 of them. But we still want to check that it's right 99% of the time, and it classifies 65% of the data. And it only takes a minute to verify this. So we do this on every run just to make certain that there hasn't been some sort of fundamental shift in how snort rules are described. So the final question, how do we actually do? So we have the numbers for how the humans were doing and how machine learning was doing. And it turns out that when you hybridize the two of them, that you do end up with better results, and substantially better results in some cases. So by being able to take the things that the machine learning algorithm has routinely seen before and have it automatically classify them, that reduces human error. By having the human then be able to manually classify all these new things, that improves what they're doing, and I suspect is also more enjoyable than having to classify 70 a day. They only have to classify maybe 10 or 15. And they already have a hint as to what the model thinks it is, and so sometimes they just go, yep, you're right, and they're done. So, yeah. To wrap up, in order to actually do this for yourselves, there are basically 6 steps. So you want to define the problem and the process up front. You really need to figure out what that is. You take your data, inspect it, understand what it is, and then clean it. That will take a lot of these machine learning tasks 80% of your time. You only get to do the fun machine learning stuff for about 20 of it. Sorry, you have to accept that. But it is really key to getting this to work. Then you get to test all your systems, and that's where the fun comes in. You could use machine learning, you may not have to, so it's important to test both and see what works. And then if you are trying to look at a hybrid solution, you then need to start defining these thresholds, figuring out what cases you'll have machine do it, in what cases you'll have human, and what cases you might even have from both. Then you get to release it, sit back, and wait for the results to come in, at which point you can then start thinking about the next thing. And at that point, this is only the first step. You might want to expand into other areas, because now you have your foot in the door on this whole machine learning thing. You might want to improve what you're doing in this particular case. So we're talking about classifying snort rules as ransomware or not, but there's more than just those two things. There's lots of different things that snort rules detect. And so we could expand this to classify a variety of things. On that note, thank you very much.
Thank you very much, Travis.
Jamie's here, he can do it.
Jamie, did you want to make an announcement on cyber? On anything in general?
I don't know whether everyone's from Cyber City.
Liar.
Oh, there he is. There's no way I could even hear you. How did John and I are here from Cyber City. So we, if you haven't already been aware, we're having a Waterloo Region's Privacy and Cybersecurity Conference next Tuesday. It's an all-day conference. If you haven't signed up already, there are only a few tickets left, like legitimately less than 10. So please do sign up. We're looking forward to hosting a great percentage of you here. We've got 10 great speakers lined up from some very cool organizations on some amazing topics. Thank you to John for organizing that. And very cool venue, Catalyst 137, if you haven't been there. So we're all locked and loaded. Really the only things we want to talk about tonight, just to remind you that there are still some tickets available. We're going to be hosting additional events in the next year as well if you aren't able to make this one. And if you have any questions, please don't hesitate to click on the website and reach out to us through email that way. John, anything you wanted to add?
We have a Slack community. Love to have more Slack in your lives because everyone needs more Slack. Aside from that, we will not be selling tickets at the door, I think we said. So if you don't sign up ahead of time, you will not be able to come in. Having said that, less than 10 tickets we should sell out this week. Yeah, we're going to have a lot of fun. This is our premier conference. We want to do it right. This is something we feel very strongly about. Obviously, as everyone here in the room is interested in cybersecurity, we felt a need to get some proper representation and kind of build this community up as we properly should. So, highly encourage everyone to come out. We're doing this for everyone. This is not a commercial enterprise by any means. God knows we're not making any money on it. But nonetheless, we do want to put on a great show. So, love to see as many of you there as possible.
Absolutely, and just one thing to add to that, if I may, is the topics and sort of the nature of it will grow and change over time. So this year we've got a balance of both technical and non-technical topics. So if you are more interested in one or the other, we have something for everybody. Also on the topics of privacy as well as security. So this is a fantastic presentation that's very technical and talks about the computer side of security. But one of the things that's very important that even I forget all the time is there's a physical side to security as well. So it's about everything together, the people, the process, and the technology. And as we grow the event over time, we'll have separate tracks. So feedback is welcome on our website about our event and what you'd like to see in the future, whether it's interesting speakers, interesting topics, interesting venues. We're looking to make this, it's for us, by us, so to speak. So let's have all the feedback we can make the best event possible. Okay, that's it. So hopefully see you all there next Tuesday.
Thank you. Did anybody have any other announcements or?
I have a question regarding your closing talk.
Yeah.
Is any idea why ML was better than the human in all the three situations? You show there.
So I think the main reason, there are a couple, but I think one of the big ones is the process was a real pain for humans, that it was hard to know if rules had been reviewed or not because of how it was set up. There were lots of prone things for typos. If you typed in the wrong number, then that's still in a lot of cases a valid snort rule, but you have no idea what it maps to. So because it was so error prone in just terms of process, that I think that meant that the data had a lot of problems in it. And that's not necessarily that the human's the problem, it's more of the process there. And then after that point, because we got the machine learning in there to really identify those inconsistencies, we were able to find them and clean it up.
It could be related also to the size of the experiment or the...
Oh, absolutely. So this was a corpus that was built up over many years where people were looking at it, but there was still the initial pass of, we had, I don't know how many, probably 30,000 or so when we started, where somebody had to manually go through and try to find all the ransomware, which they were probably doing by similar regex search like that, looking for the word ransomware or server or other things. And so there's definitely things that could have been missed during that as well.
What are you guys seeing in the way of adversaries picking up this exact technology stack and techniques, for instance, offensive ML?
So I don't know if we've seen anything ourselves. I'll direct that over to Jonathan.
So a lot of, so offensive ML, like you can see, like when you talk about that, I guess what you're talking about, you want to like do some of like the hiding and avoiding security techniques and things like that. And really what it comes down to is the same indicators are still present during an attack. You still have like reconnaissance, you still have an exploit, you still have command and control, you still have the stages of an attack go through. So it is more sophisticated, but it's, I mean, I think it's more on the level of, it's harder to detect, it's not impossible to detect, and it's a balance between like, are they trying to hide in the weeds? Are they trying to mask their signature and look like other things? I don't have a good answer. I think like the indicators remain the same. It's just it's harder to detect. So you have to have more classification, more treating things, figuring out what is actually okay.
Yeah, the reason I'm asking is we're seeing some really interesting tools pop up. For instance, Deep Drop. It's a classifier that looks at, is this sandboxed or is it not, based on an escalating PID number. So the longer a machine's been up for, the higher PID number roughly, and it takes the average PID and it created a model. It's actually pretty awesome. So we're seeing like an increase in that type of tradecraft. So I was just wondering, like, I hadn't seen it much before a couple months ago, so it seems pretty new, but it definitely seems like the blue side is not the only one with the fun tools anymore.
No, so I've gone to Black Hat, and there's been a few talks about it too, and various other places. There's been a lot of talks about how it's going to work with driverless cars, because that's a huge thing. Of like, oh my god, I don't want my car to crash. But there are a lot of things just on the security side. So there was one recently about Cylance. The big thing here is if you have access to a technology, then using machine learning on it, you can start to reverse engineer it and exploit it. So in the case of Cylance, they had access to it. It was still a black box, but they were able to start doing a whole bunch of things with different malware, and able to find that, I forget the exact specifics, but it was like adding a whole bunch of characters to it. It then passed with 100% certainty, and they could just get any sort of malware pass it. So, oops. Yeah, it's a big exploit.
I think they were modeling after Steam games actually for that particular one, right?
Yeah.
So they were taking popular Steam games, basically it's the old trick of, you know, how do you get a PHP backdoor past a file upload? You take the PNG header and you stick it in front and then you upload it.
Yeah.
It's the same thing. They just applied it to Cylance.
So
with games.
It is one of these things that if you have access to the model, then you can do a whole bunch of stuff. And at the Black Hat talk, they actually went through 3 stages. One was if the model just returns if it's malware or not, for example, if it returns a probability if it's malware or not, or if you have complete access to how the code actually works and doing that. And they showed that you can reverse engineer it all 3 stages. Not every time necessarily when we get to the very end, but basically it's that iteration. And so in terms of like our model, for example, we have machines looking at it, who's looking at it. So if somebody was trying to defeat Arctic Wolf security, you have to somehow get through both of those, and also your time between iteration cycles is rather long. Because you would try something in the network, you'd have to wait to see if you got detected, and then if you did, change it slightly, and so on. Whereas if you have physical access to the code, then you can run iterations, thousands upon thousands in parallel, etc. So it makes it a lot easier to reverse engineer.
That sort of brings to mind that, like, not just relying on one model to do this. If this was the only thing that we were doing, say like, hey, if the snort signature says it's ransomware, that's ransomware, and be like that. No, you want to like approach it through multiple vectors, like looking at multiple indicators and using that rather than just relying on Cylance, saying it's malware not. Well, Cylance says it's not malware, but I'm seeing like connections out to like Ukraine. Like I don't know.
I think I saw another hand before.
You mentioned where the confidence level is below a certain percent, introducing human analysts to confirm or deny whether somebody is ransomware in a particular case. You also mentioned that you would present the ML data, like the ML confidence level or whatever, to the user, so they go, yeah, that looks good, click. Are you concerned that by using that technique that you're biasing the human and ending up in the same place with signal, to noise problems that really ML was designed to defeat in the first place?
Yes, that is absolutely a huge thing. It's not as prominent in this particular use case because the people who were doing it were the people who were doing it before, and I trust this small subset of people to continue to try to be more analytical about it. But in general, when you're trying to deploy this en masse to people, it is definitely an issue, and it was a concern going into this as well. So we're looking at doing other things that involve far more people, and that is that question of, if we say the system says this is or isn't, that's a low-cost signal just to emulate. And if you care about people being consistent as opposed to people being right, well, just following what the machine is doing is going to make them consistent. So you need some way to actually verify that they're doing things correctly. And so some of the research that we've done and papers we've read indicate that the best way to do that is to have some sort of an expert who doesn't have access to those low-cost signals or anything else randomly review things that other people have already checked. And that way you have sort of a mentorship process already built in, because if the person who's the expert in there is finding that everybody else who's looking at it is having some sort of a problem, or there's some sort of misclassification that's happening systematically, that will catch not only if they're just trusting the model, but also if they have fundamental misconceptions about what something is. And so having that sort of review is important in manual processes as well as these ones that have been hybridized.
Human QA.
Yes, exactly. Yeah.
Did you have a situation like in image classification, they are saying you trust a model, but then you change a bit in that image and the model fails. So when you do like this evaluation of models, do you have any situation like this when you are very confident in a model and then just small change, I don't know if it applies, but the model will fail?
It absolutely applies. So I was saying before that ransomware is a great indicator, and then we sort of saw the numbers. The model still thinks that ransomware is a great indicator because the majority of times it is like one of the best ways to detect it is actually ransomware. But that being said, if you were to change a single letter in there, then it was pure as a new word, that'd be a problem. Fortunately, we aren't dealing with malicious adversaries from these third-party companies that we're paying for their threat feeds from. But in other situations, you would have to deal with that sort of thing. So there's lots of research being done into how to make your models more robust to those sort of adversarial attacks. The general idea is you have to go at it very systematically. So in our case, we were looking at two different things, if it was ransomware or not. You have to make it robust to attacks appearing, something appearing as ransomware when it's not, and then the opposite. And in the case where you have multiple things, like if you're doing image recognition on digits, for example, handwritten digits, you need to inoculate it against things that might appear as a 3 or a 2 or a 1, each individually. And so it's n, where n is the number of things you're trying to classify as. And the general research is your model performs worse when you inoculate it. And I'm going to be very specific here. It does worse on very clean data. So your very clean data set initially, when you make your model robust to sort of malicious attacks, it now does worse on that very clean data set. But it does better overall. And so you have to weigh those things as to, do you want to make it more inoculated against these things, the chance that it might do a little bit worse. You could also deploy a hybrid model where you have just the one that's not inoculated and the one that is, and then have a human review in the cases where there is 3. Lots of different ways to try to approach that situation. Yes?
What are some of the ways you've been able to improve what you already have, the results you have? For example, have you been able to take the results of feedback and train the model to improve it? Or let's say, have you been able to take like multiple data sets, let's say one from snort, the one from the IDS, combine the two and say, okay, snort gives me 97% confidence, the other gives me 98, so this is a very good hit.
Yeah, so on the first question, have we been able to learn things? Absolutely. So there are cases where there are new threats coming out each day with different words that we haven't seen before, and so the model is constantly improving and learning new vocabulary. On the second question of using two different data sets, in what we're doing in this particular example, we only had one source of snort rules, but if we had multiple, then worrying on multiple of them would change things, because there's the possibility, and we've already seen this just inside emerging threats, but different security analysts who are submitting rules to emerging threats do use slightly different language. And so in that case, when you're getting two different sources, you might even have to accommodate for slightly different words being used even when they mean the same things. And so there's some techniques you can use where you start to abstract that a layer further to get sort of features from each of those that have been normalized, and then you build a model on both of them. In some cases, you want to have completely separate models, and just accept the fact that there might be new ransomware that's added in one, and it's just going to take time to have that be detected in the second one. But there's a couple different ways to approach that.
Could you use something like NLU for that, like natural language understanding?
Yeah, and that gets into sort of some of the higher level processing that you could do. That's where, like, I touched a bit on transfer learning, the idea of you have something that's natural language processing. In this case, for BERT, was on basically all of English language, but it was not technical. And so there's lots of research being done in taking that non-technical model and then applying it to very technical domains where you have specific words, like if you're doing it on physics or chemistry or all these other things, that there are words that appear that you would never use otherwise. I don't know how often people see command and control inside their fiction novels that don't have to do with cybersecurity. So in that way, you can start training it for these more specialized domains. So yes. Yes.
I have two questions. One is, does it make any sense to give snort rules to human beings that the model is very sure of? So if a model, just to confirm that the model is not really screwing something up badly that it's very confident about?
Yes, absolutely. So we set the threshold to be 99.9%. That still means it's going to make an error on average 1 in 1,000 times. So there's a question of what's acceptable there, because humans will also make errors. But in terms of our actual process, we do have humans reviewing that too. And in general, that is a very quick thing because it's right the vast majority of time.
And then I guess my second question is, in terms of sort of the technical side of it, like, how hard is it to build these different models and try out a bunch of different models? Is it a lot of work? Is it are there toolkits and stuff that make this easy? Like, just in the side, like, did you have to hand code all of this stuff?
So
if you're exploring with this, then what are the kinds of tools you should be looking at?
yeah, in terms of tools, there are a few different, I'm going to say, skill level things that you should do, depending on how skilled you are, which tool set you should use. I would not recommend trying to write a neural network from scratch. There are lots of libraries. So in Python, there's scikit-learn that does a bunch of the basic machine learning stuff. There's TensorFlow or PyTorch that do more of the neural network side of things. But you can even go a step higher, as I was discussing before, in terms of Microsoft offers a bunch of this stuff, Amazon does too, where you just throw all the models at it. And in doing so, it's going to cost you more, but it is going to be faster in terms of it can just deploy them all in parallel and then you don't have to do any tweaking. So it is kind of that question between how much money are you willing to spend, how quickly do you want to resolve, and do you have the skill set to dive deeper? I think that it's relatively straightforward to try a bunch of the simple models. We were discussing logistic regression, and it is conceptually basically that simple, and you don't even need to understand necessarily how it works in order to apply it. It's nice to know because in your case if you're debugging it, but in a lot of these cases they are relatively straightforward for a lot of these, and I would definitely suggest starting with simpler things, getting your feet wet, understanding how they work. In a lot of cases that's all you need. You don't need to go into neural networks or deep learning, all this other stuff.
Yeah, just a comment on that. On tools, I would still recommend GitHub.
Yeah.
There's always someone who's seen the exact same problem, and there's no need for reinvent the wheel. There's always something out there.
Yes.
Like it could be something like simple, like a bash one-liner or just a Python script. That'll do the trick.
Any other questions? Yeah.
Why do you have to do all this work? Like you're paying for the list, why is it pre-categorized?
That's a very good question.
Can you sell it back for a discount?
We have actually had internal discussions, not necessarily to sell it back, but maybe we should actually make this something that we do as like a side business, where we sell like enhanced security feeds. It is a very good question. I don't know the answer. I don't know if we've actually asked them, why can you not make this better?
I can tell you can make money selling these enriched feeds. Just saying.
Yeah, you should start talking.
Or so I hear.
All right. Very cool. Well,
Mhm.
thank you very much. I guess we'll break for now.
Yeah, thank you, everyone.